All right, let's dive into something that sounds super technical, but is actually at the heart of how every single robot understands its own body. We're talking about forward kinematics, and you can just think of it as the robot's own internal GPS.
So let me ask you this. You've got a robot arm, and you tell its shoulder joint to rotate, say, 30 degrees, and its elbow to bend 90 degrees. How does the robot's brain figure out the exact XYZ position of its hand in space? That is the puzzle we're going to solve today.
And this puzzle has a name, of course, forward kinematics. The key word there is forward. We're starting with what we know, the angles of all the joints, and we're calculating our way forward to what we don't know, which is the final position of the tool at the end of the arm, what we call the end effector.
Okay, so to figure out how this all works, we first need to understand what a robot arm is even made of. Let's pretend we're building one from a kit. First thing we do, we check the parts list.
So fundamentally, a robot arm is what's called an open kinematic chain. That sounds way more complicated than it is. All it means is that you have a series of rigid parts, or links, think of these as the bones, and they're all connected by joints, which are like your elbows and shoulders. The chain starts at the base and ends at the hand. It doesn't loop back.
Now, what's amazing is that pretty much every robot you've ever seen, no matter how complex it looks, is built from just two basic types of joints. You've got your revolute joint, which is just a simple rotation, exactly like your elbow, and then you have the prismatic joint, which is a straight-line sliding motion, kind of like a telescope extending. That's it. Every robot is just a clever combination of rotations and slides. Okay, so we have our parts, links and joints. But think about it. If every engineer just connects them however they want and describes them differently, how could we ever write a single piece of software that can control any robot? It would be total chaos. We need a standard, a universal blueprint. And this really is the core of the problem. Without some kind of standard, every robot is a one-off custom job. You'd have to invent a whole new set of formulas from scratch for every single robot. Talk about inefficient. There has to be a better way, right? And there is. It's an incredibly elegant solution called the Denovet-Hartenberg Convention, or just DH for short. It's not a physical part, it's a set of rules. It's a universal algorithm that tells you exactly how to attach a little coordinate system to each piece of your robot, and to do it the exact same way every time. It is our universal robot blueprint.
So how does this blueprint actually work? Well, this is the beautiful part. It turns out you can perfectly describe the shape and connection of any piece of any robot by taking just 4 specific measurements. That's all it takes. 4 magic numbers.
And here they are, the famous DH parameters. First you have A, the link length. That's easy. It's just how long the link is. Then there's alpha, the link twist. Imagine taking that link and giving it a little twist along its length. Next up is D, the link offset, which is like a sideways shift. And finally, theta, which is the actual joint angle we control. Any connection on any robot can be described perfectly with just these 4 numbers.
Now, to make sure we all measure these numbers the same way, the blueprint has some very strict rules. Rule number 1 is the big one. The z-axis always points along the axis of motion. So if it's a rotating joint, z is the axis of rotation. If it's a sliding joint, z is the line it slides along. Rule 2 says the x-axis has to point a very specific way. And finally, the y-axis just kind of falls into place based on the other 2. You follow these rules, you get it right every time.
All right, that's enough theory. Let's get our hands dirty and actually see this in action. We're going to build a super simple 2-link robot, one that just moves around on a flat table, and see how these rules and numbers get us to the final answer. The whole assembly process is always these 4 steps. First, we'll assign our little coordinate systems our frames using those strict DH rules. Second, we'll measure our 4 magic numbers for each link and pop them into a table. Third, we'll turn each row of that table into a bit of math called a transformation matrix. And last but not least, we'll multiply them all together. So after we assign our frames, here's the DH table for our simple little arm. For the first link, the length A is just L1. Now, because our robot is totally flat, there's no twist between the joints, right? So alpha is 0. There's also no weird offset, so D is 0. The only thing that changes is the joint angle, theta 1. And you know what? It's the exact same story for the second link. See? Pretty straightforward. Okay, this is where the math magic comes in. We take the 4 numbers from each row of our table and we plug them into a standard formula. This spits out something called a transformation matrix. Don't worry about what's inside it. Just think of each matrix as a single command that says, okay, from here, rotate this much, and then shift this much.
And now the final step, the chain reaction. To get the total transformation from the base, we'll call that frame 0, all the way to the hand, or frame 2, we just multiply the matrices together in order. We take the transformation for the first link and we multiply it by the transformation for the second. The order here is absolutely critical. You're chaining the commands together.
And when all that matrix multiplication dust settles, this is what pops out. I know, it looks like a formula from a math class, but look closer. These equations give us the exact x and y coordinates of our robot's hand, and they only depend on things we know, the lengths of the links, L1 and L2, and the angles of the joints we're controlling, theta 1 and theta 2.
And here's the really cool aha moment. If you just drew this robot on a piece of paper and used basic high school trigonometry to figure out the position of the hand, you would get these exact same equations. This proves it. Our big, fancy, universal system for any robot gives us the simple, correct answer. It absolutely works.
Okay, let's just zoom out for a second and make sure we really get the big idea here. We've been in the weeds a little bit, but what's the one thing you really need to take away from all this?
If you remember one thing, make it this. Forward kinematics is really just about describing each step of the robot as a small transformation, and then multiplying all those transformations together in a chain, starting from the base and working your way out to the end. That's the whole game.
And hey, for any of you who are thinking of trying this out, just a friendly heads up on some common pitfalls. The rules are simple, but you gotta follow them exactly. Messing up the z-axis is probably the #1 mistake people make. Getting the sign of that twist wrong, multiplying in the wrong order, these little details can throw your whole calculation off, so just be careful.
So, we've figured out how to find the hand's position if we know the joint angles. But think about it. In the real world, you usually have the opposite problem, don't you? You know where you want the gripper to be, and you need to figure out what the joint angles have to be to get it there. So, how do we run this entire process backwards? Well, that is a whole other story.